Hello, everybody. Welcome, welcome, welcome. It is I, Mark D'Antonio, and I am here with Daryl Mason, of course. Hello, Daryl. How are you?
Hello, Mark. I'm good. How are you? Hello, everybody.
I'm doing fine. I'm doing fine. It looks like we've got a really good night here for the moment. So I'm hoping it's going to keep going. The only thing is I have to do a couple more little changes here, and then we can do this. So what I want to do is figure out where one of my objects is. Oh, well, maybe that's why. Okay. Yeah, that's gonna change. There we go. Oh, boy, look at me go. Sorry about that, guys. I'm really kind of large up there. That's not what I was expecting. So let me just get rid of that and tone it down a little bit. Alright, so I'm melting. No, not yet. I want to be melting. I want to change the size of that thing. That should be it. Oh, wait a sec. Why can't I change me? Hello, go away, you. First things first. I'll lock you up. And now that it's locked up. Well, anyway, hi guys. I'm a big green guy in your screen right now. I'm just huge. That's not good. I will fix that. Um, First things
I
first.
see. There's a big gray box over on the upper left where your keypad usually is.
Yeah, that's this here. It's gonna go away. Yeah.
There it
Okay.
is.
So now it's clear, and now let me see here. So tonight, guys, we're waiting for it to get fully dark, and what we're going to do is we're going to be checking out the supernova again. It's actually right here. You can see it right there. This is the galaxy, and it's not fully dark yet, but as it gets darker, we're going to check it out. I want to welcome all of you guys here, and Daryl, I was asking a question before we started, and I didn't get to hear an answer yet. When I had the crowd, there were 200 people out in the audience watching, and I said I couldn't get you on with us because the Skype thing wasn't cooperating out in the field. I fixed that since then. Um, and I asked them to say hello to you, and they said, "Hello, Daryl. Did you hear that?"
I don't remember. I don't think I did.
Wow, because it's on the stream. You can hear it.
Okay.
They said, first of all, they all said hello, and then they all said that later when I asked them to say that to you.
Maybe I just missed it, or I don't
Well,
know.
it's
Things are
possible.
things are moving pretty fast at the time. I remember.
Yeah, it was going pretty wild. But that's all right. That's okay. That is okay. All right, so and as I said, we're just waiting for it to get a little darker, and it will, and then we will move on. Hello to everybody who's here. I see a bunch of people already showed up. Rascally Rabbit's here. Izabela's here. Papa Tom. Michael Hedrick, how you doing, man? Good to see you. And Cyclone is with us. And I saw, who did I see down there? Someone else. Daniel, how you doing, man? Daniel's with us. And Alice Pooper's with us. And we have a few others actually that are joining us. We got a lot of people. Lady B Elements, Lady 5 Elements. How you doing? And I think right now that's what we have right now, but that's gonna change as more people join. There's more watching right now than are listed in the chat, so that's pretty cool. That's always the case. We always got a lot of good people with us. So that said, I am really excited that you guys are here, and I am going to try a test exposure here just to see what a 12-second shot of the galaxy will show us. I've said this before, but I'll show you again. Okay, we really only care about a couple of parameters here. There's one here. This is the exposure time, highlighted by the arrow, and then the gain is over here. And the gain is the sensitivity of the sensor, and the exposure is how long that sensitive sensor is going to be exposed to the light coming in from the telescope. Right, so that's what we want to do. We're going to actually do some more of that right now, and I'm going to take this 12-second shot, and we're going to tell it to go. We're in night vision mode right now, and I'm going to get out of night vision mode and go into stack image mode. And then that's the old one when it was still sunset. You could see this red glow from the sun setting. All right, and down here is our progress bar. When that reaches the other side, boom, we get our colors. And you see the blue hump here, the green hump, and the red hump. These are the colors, and they have to be all aligned with each other for us to have the proper color. So I'm going to do the color alignment right now. Boom, now they're all together. Now these are our bars that pick off the different levels in here. So if I move these over, you'll see now that the image is going to change. Look at that. Okay, this one here is our dark level, and this one here is the middle level. All right, mid-level brightnesses in colors. So if I move that to this side, you'll see it'll get dimmer, and we'll also lose image, detail in the galaxy at that time as well. However, this is Measure 101, and you can see we have a little sunset around here. If I just let it auto decide what it wants to do, then this is where it goes. All right, so you can see right there, that's the supernova, but we'll zoom in a little on that so you can see it. All right, because that's kind of important to do. Now, the more we stack, the better the galaxy image will look. All right, this modeling in here. This modeling goes away as soon as we stack more images. We've stacked 7 so far. All right, but for the record, and just so you can see, one thing that we want to notice right away is the supernova inside this red box. There it is. And this is live. Hey, C&D boy, how are you? Yeah.
I mentioned yesterday that Sky and Telescope said that the supernova has dimmed just slightly, like 0.2 of a magnitude. Looks the same to me.
Yeah, I think it does look the same right now, but you know what? That'll change. We're gonna be waiting for that. I'll tell you that. We will wait for that. All right, so let's move you out of the way. So let's let these come in, and then we will do our thing here in just a minute. Okay, a few more images. We've got 12 done here. This is just a 12-second shot. All right, so even in 12 seconds, look what we're getting. We're even picking up this faint galaxy here. You know? But you still see the red border. That's because the sunset is still happening out there. So we're catching the galaxy while the sun is still illuminating the horizon a little bit with a red afterglow. And that's what happens, unfortunately. But that's all right. That is just fine. Okay. So we'll give it a second to...
They say you're not appearing on the screen, Mark.
I know I'm not. I'm working on that in the background here.
Oh.
I'm in the test one, but I'm trying to get it to work outside.
Okay.
Trying to figure it out, but thanks, guys. I am aware, and I will get it to work here soon. gotta do a quick sign in here.
Betelgeuse is actually behind the sun now, folks. We can't see it.
Somebody asking?
Just a lot of general talk about Betelgeuse.
Oh, yeah. Betelgeuse, our favorite supernova. Coming favorite supernova. I think the time will be when we'll be able to say that, and we will say that. What on this thing?
I guess I'm old-fashioned. I'd be sad if Betelgeuse blows up, when it blows up.
Oh, I don't think I'd be sad. I think I'm going to be just so excited to see what happens. I really will. It'll be very exciting.
Yeah, well, hopefully it'll leave a pretty nebula in its place.
Oh, I imagine it will. I imagine it will.
And it's just the idea of Orion's appearance changing forever.
I know.
Such a big, notable star.
And that's actually it's actually quite a notable change it would go through as well. Indeed. Alright, so video capture, okay. Alright, I am going to get rid of something and then start it up again. No, not that. So we're waiting. We're just going to wait. The sky's getting a little darker out there, but I thought I would start up early and have you come on in. Yep. Hey, Rocket City Astro is with us. Nice to see you, man. Are you imaging anything tonight? Alright, let's do this. Waiting a little bit.
Cyclone new stars will inevitably form with components from the supernova Betelgeuse. Not so much like we could make them, but you know, just the nature of things. They'll supernova remnant materials will be floating around in space, and they'll ultimately wind up in other stars. That's how it works.
That's correct. So I'm wondering why this is doing this. You guys saw me there for a moment. I'm still working on this. So what I'm going to do is I'm going to clear this here, and we're going to pick it up again and just start over again, because I want to see if we've lost our sunset light yet. So we'll clear it and get going, and this next one will be in momentarily. In fact, now. It's still a little red, so we got to wait a little longer. We have about 20 minutes until the sun is 18 degrees below the horizon or so.
Have you run a focus yet?
Yep. I've already done the focus.
Got your T-comp on?
I do not yet. I probably should. It doesn't change much initially. You know, it takes over a couple hours for the temperature to change so much that it makes a difference. Philos Farrar, how are you? And we have Creeptasia, nice to see you. Michael Galea, how you doing? Yep. All right. Neat.
Alice, I read somewhere that if you're talking about the supernova in M101 we're looking at,
Yes.
they think it was maybe about 12 solar masses before it exploded. If I remember right, the article in Sky and Tell, I think that said that they think they identified the star in the galaxy prior to its explosion.
Yeah, I think they were able to do that because it was a fairly prominent star.
Oh,
Indeed, it was.
give me a second, I'll go look.
All right. Uh-oh. Our session was interrupted on the other side. All right. Well, we're going to figure that out. One second, guys.
Maybe it wasn't Sky and Tell.
Oh,
I don't see it there now.
okay.
They do have an article about how soon will Betelgeuse blow, though. I'll post that instead.
All right. Okay, I'm going to redo the
Whoops.
share here for you
Okay.
because I believe that you didn't. Did you lose it or no?
I lost it, yes.
Yeah, well, now it's back. Okay, good.
Okay, there it is.
All right, let's color correct this. And let's do a process on it to try and bring that out. Oh, yeah, we're starting to lose some of that. Okay, there we go. There's some red there. We'll let that go for a bit and see how far along it goes.
Cyclone, you wouldn't boil. You'd be gone too fast for it to boil.
Oh,
You'd vaporize.
why don't you read the question? So,
Yeah. Would your body boil if you were in the sun?
oh, well, then you'd be exposed to, 10,000 degrees of temperature instantly, and that's the plasma temperature at the surface. So, yeah, you would even. I don't think you'd even have time to feel anything, to be fair.
Yeah.
Let me back this
There
in
are
here.
some interesting videos, volcano videos on YouTube. Some where they chuck trash into a
Oh, yeah.
active volcano, and
Urta Ale.
you can imagine, like what happened when Gollum fell into the Lake of Fire in Lord of the Rings.
Nice hobbits. Yeah. Yes, indeed.
Alice, yes, it is. It's M101, if I remember right. It's about 1 trillion suns. It's maybe twice the diameter of the Milky Way. I'd have to look it up. It is larger than the Milky Way, though. I do believe.
Mm.
Yeah, it's about 1 trillion stars, 1,000 billion stars.
That's a lot of stars.
Yep. And
What's going on there?
Diameter is 170,000 light years. Milky Way is about 100,000, they think, so it's nearly twice the diameter.
That's pretty big. That is really, really large. Hey there, Sam S. Alright, so tonight what we're going to do is a few other things too. We're going to be looking at this one, of course, but we're also going to be, as soon as it gets fully dark, we're going to be checking out some of the other objects that are approaching and to herald the start of summer, astronomically.
It's only 11 days away.
I know, it's something else. Okay, so here's our galaxy now. Let's throw in an enhancement. Okay, so now the galaxy looks sharper. You can see really many details. That's cool. That's really cool. I like that. That's very cool. That's neat. Alright, so
Cyclone asked if we might look at Polaris.
that'll be tough because we would have to point the telescope in a very different direction to do that. We're straight back along its axis. And although we might be able to do that, I'm not sure how that would work. I think we can, but in fact the telescope would be pointing back just a little bit more than this, so we might be able to do it. I've never actually pointed a telescope at Polaris, believe it or not. Which is
Never?
Not usually. I mean, except for aligning once or twice. I've never had to point it at Polaris again. Which is
Polaris
kind of
is actually a double star. It looks interesting.
It is. Yeah. Yep. And this is Measure 101 Galaxy with Supernova 2023 IXF. And of course.
There's a thing with pointing telescopes, people. If you have a Dobsonian telescope, it's a so-called alt-azimuth, altitude and azimuth.
Yeah.
And if you have the altitude pointing at 90 degrees, that is straight up, it gets hard for the telescope to be able to follow things that are directly overhead. Its slew rate becomes infinite, so they say. And something similar happens with equatorial mount telescopes, like the fork mount on Mark's telescope. When you're pointed instead of straight up, because it's equatorially mounted and lined on the North Polar axis, when you try to point it toward Polaris, which is very close to the North Pole, it again is sort of like an infinite slew rate, and it can be hard to get it and keep it in view. Once you get it, but it may take a lot of bumping around for the drive. Hello, Petita.
Oh, Petita's with us. Hi, Petita. Nice to see you here.
Hello, Prowl.
Prowl's with us
Prowl,
now,
we
too. That's
mentioned
good.
earlier the supernova may just barely be starting to dim now. It was reported the other day that it's dropped maybe 0.2 of a magnitude. It looks the same to the eye, but it may have begun dimming slightly.
Very nice. Sorry I'm not visible on the screen tonight. Not sure why, but I tried to figure it out, and I'd rather just bring you some cool astronomy, and then we can worry about that for another stream. Not a big deal.
Cyclone has a question for you.
Let's see. Oh, that's for Mark M-E-R-K. I'm Mark M-E-R-C, so I'm off the hook. Just kidding, Cyclone.
Yeah.
In the show, you're in what UFO video? In the show, you're in what UFO video is most convincing to you? Oh, that's a tough question because, to be fair, the new season of The Proof Is Out There just started, and I don't want to give it away. So the Proof Is Out There is on History Channel, and I'm pretty sure that you guys probably have it in your locale. There's no reason to expect not. So I'd like to have you check it out and see what you think of it before I start spoiling all the fun. Because I won't be spoiling all the fun. There's actually a very exciting case that we had where we couldn't explain, believe it or not, for this season. So I'll let you wait and see which one that is. Oh, by the way, I just want to say that the issue. Let's see, where am I going? I had 4 things in my head at once. I do 5 things at once doing this, and had 4 things in my head, and one of them just went away, and that was the one I wanted to tell you. It'll come back. But for now, I want to cut over to Izabela. Izabela has some interesting questions that she has asked, and she asks, what are isotopes, and why are they different on other planets? Are they reliable evidence or ET materials? Very good question. And let's talk about that. In fact, having this galaxy image up is actually quite a good time to do that. And Daryl can chime in too, because I know he knows a few things about isotopes as well. But when we look at this galaxy, okay, we're seeing a lot of material, atomic material. We see a lot of star clouds. Those are stars, and the stars have elements in them from our periodic table, sure. Now, how those elements were made is that they were made in the stars. And everything that makes you up as a human being was once made in the heart of a star. All right? So the calcium that you have in your bones, it was made in the heart of a star larger than the sun, as a matter of fact. And the magnesium that you have, again, made in a star larger than the sun. And anything beyond carbon and some oxygen that's in your body was made in stars larger than the sun. So there's an awful lot of them out there. And so these elements are made by a process in a star called neutron capture. And neutron capture starts with, as Izabela asked the question, an isotope. So let's suppose we have helium. And helium ends up capturing, it has 2 protons in its nucleus and 2 electrons circling around it when you have a neutral helium atom. And now, let's suppose that a neutron has no charge. A neutron ends up in the nucleus of the atom. This happens quite a bit. Okay, now, the neutron that's in the nucleus of that atom stands a chance to undergo something called beta decay. Beta decay is something, for those of you out there who like quantum mechanics, is moderated by the weak force in quantum mechanics. If you don't understand it, don't worry about it. Just understand that we are talking about protons in the nucleus with an extra neutron that shifts right in, and now it's sitting in there. Now that neutron can be converted to a proton through this thing called beta decay. But when the neutron is in the atom, all right, or let's say in the nucleus, then that neutron makes that helium atom an isotope now. An isotope is an atom that has neutrons in its nucleus of any kind. Because atoms in general do not have neutrons in their nucleus. Okay, the base atom, a hydrogen atom, is one proton, one electron. Okay, and when you have those atoms like that, you will not have any neutrons in the nucleus. If they end up in the nucleus, they end up there for a reason, and that reason, as I said, has to do with something called neutron capture. It's a way that our star makes other elements a long time. It takes a long time. It's a way bigger stars do that a little faster. And these elements are forged through the changing of a neutron into a proton. Now, if you change a helium nucleus that has 2 protons and 1 neutron into a nucleus that has 3, well, then guess what you get? Anybody know?
Say that again.
If you actually have a helium, if you have a helium nucleus which has 2 protons in it, and you add a neutron, and that neutron gets changed into another proton, so now you have 3 protons in the nucleus. What has that helium atom changed to?
Lithium.
You got it. That's the next element in the periodic table, and so it goes. You can have a silicon atom changed into a phosphorus. You can have phosphorus changed into sulfur. Okay, and then chlorine and argon, all the way up in the periodic table. And some of those isotopes are more stable than others, and some of them are less stable. So they only last for a short amount of time, like beryllium. Beryllium goes away fairly quickly when you get an isotope of beryllium. All right, and same with lithium. So they don't tend to make lots of lithium and beryllium. That phase comes and goes very quickly. All right. However, when a boron atom has an extra neutron in its nucleus, boron is actually, it's number 5 on the periodic table, and carbon is number 6. So a boron atom could go through beta decay to make a carbon atom, and that carbon atom has very stable isotopes. When you put neutrons in it, it has some stable isotopes, and this is why carbon is so prevalent in the universe, because when it's made in the star, it's made in a stable manner. And consequently, you also can get nitrogen out of that, and the next one in the periodic table is oxygen, and the oxygen atom also has stable isotopes. So this is something that is how our atoms, in the periodic table are constructed through the hearts of stars, and beta decay is a way that this happens. Now, that's also called the S process, or the slow process. Again, terminology doesn't matter, all right? And so I think when we talk about it, we're looking at a very interesting process that takes place in the hearts of stars. And thus, because of the weak force, WEAK, the weak force, it's a fundamental force, that actually has W and Z bosons, they're called, particles, that facilitate changing a neutron into a proton. If I go deeper than that, we got to talk about quarks and how each particle is made up of 3 quarks, and one of the quarks gets changed from an up quark to a down quark, vice versa, to make it into different particles. And this does happen. And so when it happens, we end up with this new particle. And bam, now we got a new nucleus for a new atom. Some of it's stable. Sometimes they go back to the old thing. Sometimes they stay at the new thing. And this is happening all the time in stars. They're making an atom or making a nucleus of a new atom, and then sometimes they'll decay back to the other thing. And it just keeps going back and forth until the net result is you get more atoms down the line in the periodic table. Okay? And then when new stars are formed, they're made with the junk created by the old stars from which they're made. So our sun has calcium in it. Well, our sun didn't make the calcium so much as it had it in it when it was made. How do we know? We know that because the calcium is visible in the sun's spectrum. It's on the outside of the sun. It's in the envelope of the sun. It's not in the core of the sun that we can tell. All right. So that's how that works. All right. Now I know it's a long, drawn-out answer, and Daryl, add to it if you like, because I'm gonna stop talking now.
Okay, I will add just a little bit. Izabela, you probably heard of carbon-14 before. Carbon has various isotopes, and the only difference is the number of neutrons in the nucleus of the atom. Carbon-14, in particular, that isotope of carbon, that's what's used for carbon dating materials. You've heard of, surely. Like they dig up some ancient object and to find out how long ago it was alive, like a fossil or something. They will carbon date it, detecting how much carbon-14 is in it, and through the magic of science, the wonders of science, they can get a good idea of how old that object is. Neutrons, isotopes get to be more important when you get up into the heavy elements, like uranium, for instance. There are various isotopes of uranium. There's a Colorado answer for uranium. It turns out over in the western part of the state, in a place called Uravan, is where they mined the uranium that was used in the atom bombs that ended World War II. Uranium-238, that's its atomic weight, is pretty prevalent. Uranium-235, if I remember correctly, is the one that's got all the juice in it that they made atomic weapons out of. And that difference in weight of 3 from 238 to 235, those are neutrons, because the uranium itself has 92 protons in either case. And to get from 230 to 235, Mark could say better than I, but there are probably physical processes where they can whittle it off. One way they've done it in the past is they use centrifuges to separate out the different isotopes. And there's a lot less U-235 than there is 238, but they can concentrate it using isotopes. The other part of your question, isotopes varying from planets to planets and ETs and all that stuff, I don't think I could really answer that. I would say it doesn't really matter, or it might matter a lot. I'm just not qualified to say. Isotopes might be different on different planets, depending on physical processes. That's a little above my pay grade.
Well, I can say that it's well known that there are certain isotopes that can only form in interstellar space, and that we don't get on this planet. And there are certain transitions within an atom of energy levels, transitions with electrons that can only happen in space. One of them is the doubly ionized oxygen, O3. O and then Roman numeral 3. So doubly ionized, that is what's called a forbidden line when you see it in the green that we see in some of these planetary nebulae. It only occurs in very, very thin gas structures out in the vacuum of space, out in the thin, rarefied gas that's expelled from the stars as they expand in their death like that. Yeah, Gladys says, I can't believe astronomy involves chemistry, too. She's a sad face. Oh, you know what? chemistry is actually the coolest thing if you give it a chance, all right? Because in astronomy, almost everything we learn about has to do with a chemical reaction that causes something. Okay, the light you see from these galaxies, this is caused by reactions in these stars. It's called nucleosynthesis, right? However, the light of these nebulae that we see in some of these galaxies, in fact, if we zoom in here, I can actually show you. Let me actually move up a little bit. Now that we've done this, let's move in here. Okay, see, let me go color correction first. There we go. All right. So now, if we look in this galaxy, you'll see that right here, there's a green thing. See that green thing? There's another one here, and there's another one here. All right, and there may be some here, but these green things are potentially supernova remnants, and they glow green because of that forbidden line I was telling you about. Oxygen is doubly ionized as a very, very, very sparse gas within the galaxy in this expelled matter coming away from the supernova center. And that expelled gas is doubly ionized by the hot remnant of that supernova explosion, the neutron star or the pulsar, when it has these lighthouse beacons that are spinning as the star spins at rapid speed. A pulsar and a neutron star are the same thing. It's just a pulsar is a kind of neutron star. So, but that's an example, see, of that green glow right there, potentially.
And when we look at planetary nebulas, that telltale green color is the very same thing. It's doubly ionized oxygen.
Think about the dumbbell nebula that we often see. Actually, I have another idea. Let's first of all save this.
There's a great big green thing over at about 10 o'clock from the galaxy, upper left.
This here? Or this?
No, that one.
Yeah.
That's real because we've seen that many times before.
Yeah, it is. It's absolutely real. Okay, here's what we're going to do. M101 with Supernova 2023 IXF. And if you go to skytourlive.org, which you see right here, I'm using my mouse to point it out now. Skytourlive.org will allow you to go to the server where these images we're taking are going to end up probably within about 30 seconds. All right, so we're saving this image exactly as seen. And it's only a 12-second image because if you notice, this telescope runs 25 times faster than other telescopes because of our setup. And right now, anyway, it's the only telescope in the world with this configuration. All right, there are other telescopes that can do the same kind of thing, but this is the only Meade telescope of this kind that has this on it. It's the only one. It's a prototype, and it's performing better and better and better. Izabela pointed that out another stream. Hello, Cindy Murphy. Cindy Murphy says, the periodic table I learned in 1970 was different than now, and I remember my teacher saying, let me see if I can see the rest of this because it's a little off. Alright, let me see here. Alright, I know she's saying, I'm trying to see the rest of what she wrote. Here we go, okay. And she says, I remember my teacher saying the empty spots will be filled when discovered. And it fascinates me. It just explains. Oh, well, you're welcome. She says it explained well. Keep in mind that there's something else that we're fighting. Atoms can only be a certain size. And why is that? Because an atom can only have a certain number of protons in its nucleus, because there's another force besides this weak force which makes atoms, the nuclei into one to the next. And that's called the strong force. It's the force that holds positively charged protons together in the core of a nucleus. All right? And that positively charged proton wants to repel from every other proton. It's like trying to push the north poles of magnets together and imagining a force strong enough to push them together and hold them there forever and ever. And that's what the strong force is. It's the strongest force in the universe. And that strong force is very important because the strong force is something that, when the protons are crushed together, as the nuclear core, the center of an atom, as it has more and more protons, the nucleus is getting larger. And you can imagine a point where the strong force finally wanes and goes away to the point where atoms, or the protons, can no longer be held to each other after a certain size. The outer ones just can't be held. And believe it or not, that size is at around 118. And right now, our periodic table is at 118. So technically, we can't have any more atoms with any larger nuclei than 118 protons in the middle.
There's some conjecture. Maybe you were going to talk about this, the so-called island of stability, I think it is.
Yes.
Some scientists think there may be a so-called island of stability higher up than the 118, where atoms once again would become stable, even at higher counts. They haven't found it yet.
Right, they haven't found it, but it may actually be a real thing, and it's kind of cool to think about. But yeah, this is a beautiful. Quantum mechanics has not stayed the same ever since it began. Every year, something new happens. Okay, every year, and the thing that's happening now is that we are finding that in the nuclear realm, we're finding that certain other things within atoms are changing. Certain other technologies are presenting themselves. Like, if you think about all those fundamental forces, okay, there's 4 fundamental forces, right? The 4 fundamental forces are the weak force we talked about, the strong force I just talked about, and then we have the electromagnetic force, which is light. And then after that, the 4th force, and the weakest force, believe it or not, is gravity. You might say, wait a minute, gravity can hold things from so far away. Yes, but it's the weakest force. It acts at a long distance, but it's actually quite weak compared to the strong force, which can hold positively charged protons together, but only out to a certain radius. Okay? So it's pretty neat. The thing with gravity is that it's different from the rest of the forces because every one of those other forces, the weak force, the strong force, and electromagnetic force, those can all be characterized as dual objects: a particle, a proton, and a wave function that describes the proton. All right, and same thing with the strong force. All right, we can describe these gluons as a particle, and with a wave function to describe their behavior. Light is both a wave and a photon. All right, but gravity, that weirdo, is only so far a wave. We've only seen the gravitational wave. We have not seen a gravitational particle, which would be the graviton. And at CERN overseas, they're actually building another accelerator to study a certain type of particle that could, and this is the one I lecture on, actually been lecturing on this one around the country, a particle called a Kaluza-Klein particle. Kaluza, K-A-L-U-Z-A, and Klein, K-L-E-I-N. And the Kaluza-Klein particle could very well be a particle that could make the difference in stellar travel. And the reason is long-winded, and I won't get into it now, but I'll save that for another stream. And I'll actually do a little bit of that talk that I give so you can actually see it. Once I get back on the screen, it'll be better because then I can do a few diagrams and things that'll help you. So we might be able to go interstellar in about 150 to 200 years in a way that we won't have to traverse. Now, this is the killer. If we want to go from here to Alpha Centauri, we wouldn't actually go directly from here to Alpha Centauri. We wouldn't cover the intervening space between Earth and Alpha Centauri, we would actually do a fifth dimensional travel, where we'd punch out of our 4 dimensions and then punch back in over near Alpha Centauri. And you might say that's just science fiction. Well, it was until it wasn't. And that's something that's coming. And in order to generate those special Kaluza-Klein particles that can accomplish this, we just need, believe it or not, a fusion reactor to do it. And what just happened recently with Lawrence Livermore, Daryl, you know, they started a process where they could create fusion and create a somewhat sustained fusion reaction. Now, it wasn't exactly what we're looking for with fusion reactions, right? It wasn't a stable reaction that was self-sufficient for as long as they wanted it. They had to put a lot of energy in, and they didn't do that classic break-even where they got more out than they put in. But they got to the point where they could actually create a reaction that was ongoing. All right? Now, that's new. We've never done that before. So, in other words, fusion reactors are just a Lawrence Livermore discovery away. Now, that means something, doesn't it? This tells us that we are going to be on the precipice in the next few years of having a fusion reactor that could create these special particles that could give us the capability to travel into the 5th dimension of space, okay, and do this Kaluza-Klein stellar travel. And that depends also on something called string theory, and that's a whole nother talk. But I just thought I'd share that with you while we're rounding out at 175 shots here. So we'll save this one more time, and then save it exactly as seen. And there's our supernova right there.
Folks, if you'd like to learn more about isotopes and heavy elements, there's a YouTube channel called Periodic Videos. It's put out by the University of Nottingham in the United Kingdom.
Yeah, they're very good.
It's about chemistry. They're very interesting and entertaining. This old guy, I believe he's been knighted now. His name is Martin Polyakov. He's like the professor of chemistry at the university. He's got a big bushy white afro, a little old English guy, big old bushy head of white hair. It's a funny channel sometimes, and they talk about all the very heaviest of heavy elements and the discovery of new, what do they call them? Transuranics, I forget, the really heavy elements.
Yeah.
And the deal Mark alluded to earlier, where they get to the point where they're so big and heavy, up past up to 118, that they're unstable, and their lifetime is like milliseconds. Some of them are so short before they just cannot hold it together, and they basically fission and turn into something else.
See, now, folks, from what we were talking about before, doesn't that sound pretty much exactly like some of this decay we talked about, where one nucleus turns into another? And I mentioned it could go either way. This is exactly what Daryl's talking about. It's one of those conditions. So you see, there's a huge use for discussions of these isotopes. And when you look into space, that's a fertile breeding ground for many different types of atomic reactions, most of which we can't get on this planet because under an atmosphere, under this amount of pressure, you just don't get that, where the gas is so dense compared to interstellar space. Now we're looking at this guy right here. You don't have any idea what that is yet, but I am going to tell you. You got it. This is a nebula that oops, did I just do that? I didn't want to do that. Okay. Sorry about that. I got to get back to it. I made a little bit of a mistake. That shouldn't have been. This should have been. Yeah, I need to be smaller jump. All right, so I end up shooting myself way over there. Let's just go back here and go back to the center there. All right. Alrighty, so now, all right, So here's the cat's eye. And now that I won't be shooting us way the heck away from it, I can take us, just head up north a little bit, and then head to the west a little bit, center it up. Because I want to show you, this is a planetary nebula called the Cat's Eye Nebula, as Daryl just said. And it just looks like a blob right now, like a big star. But I want to show you what happens. I think it's dark enough to do this now. Okay, and there goes a satellite zinging right through down there.
If you've ever watched Star Trek, folks, you've seen the cat's eye. They one of the early Hubble images, I think it was, they used to use like on monitor displays.
That's right.
Star Trek Next Generation.
That's right.
And there's, of course, the original Hubble image of the cat's eye. It's a nice planetary. It's very small, far away.
Well, it appears small. However, let's watch, because it has a lot of detail in the outer rim that's fascinating. You can actually see these little spokes. It'll take some coming in here, and let's make sure it's dark enough. Okay, let's do this and get rid of this, and boom. So there you see the cat's eye right there, and it has this little bright oxygen 3 emission right there. That's really fascinating. And we can zoom in a little bit, and it'll get clear as a few more exposures come in. We have another one coming in momentarily. See this colored modeling? Look how it goes away with the next image. Look at that. Suddenly it gets clearer. And look at see these spokes in here? You can see that it's got stuff going out. And this is an area where there's like a knot of material. It might be that there's another dense area out here, and as this gas was expanding out from the center of this dying star, it collided with the interstellar medium, slowed down, got hot, and again began to glow. The glow is caused by ionization, and that's what oxygen 3 is. It's an ionization process. So this will be a little clearer here as we move forward. Let me see if I can bring it a little better. Yeah, you can see a little more now. See how it's almost round? This shows that it kind of expanded at sort of a regular manner, which is really cool. So we'll take a few more shots of that. Yeah, this one's awesome, Michael. Michael says, oh, cool, don't remember this one. We haven't really looked at it a lot, you know. And the green, as Daryl points out in the chat, is the color of that ionization process that occurs with oxygen atoms out in a nebula like this. Now, I say oxygen atoms because inside of a star, there's no atoms. The stars have such hot plasma that all of the atoms are turned into just nuclei. The electrons are shot right off of from the temperature and ionization. But in the outer atmospheres of some of the bigger stars, especially stars that this one was, it was a red giant at one point, and as it expanded outward, this particular star got larger and larger and larger, and then molecules could form in the outer atmosphere of that star. And those molecules, very important, because those molecules were able to form oxygen atoms. Back to, instead of oxygen nuclei, it attracted the electrons to make it an oxygen atom again. And as the electrons were energized off the atom by the hot temperatures of the stellar core that's in there, they would then come back in and rejoin the atom. That's called recombination. And when that happened, we saw a light that's given off at that point. And that light that's given off at that point where the electron comes back into the atom, as it loses energy, it gives off light, is a green one. And that's the predominant color that's given off when it does that. So that's pretty cool. That's how this works. And we'll soon be able to see the dumbbell, as Daryl was mentioning in chat. And it's pretty cool. Let's zoom in a little more now and maybe pull out some more detail, shall we? Let's go in here. So now you can see there's a little dark lane in here. It's actually really interesting, and you can see these little spokes I was telling you about. See that? Yeah. Then over here there's something, and over here there's something. They may be galaxies, they may not. But let's see if we can reduce some noise and pull out a little more detail. Maybe if I pull this to this side, get a little brighter, you'll see the green, and then move this over. This is called a push. And you can see now a lot more detail in there. And then we just pull this over, darken the noise out a little bit. This is what we do as astronomers, you know. We play with our images to try and make sure that they're give us as much information as we want. And many times the image that we like is not the one you'd like, you know, because we tend to look for other things, and sometimes we will settle on an image that doesn't show as much of a pretty picture as an informative picture. But for tonight and for everything that I'm doing with you, it'll always be the pretty picture. So right here you can see the telescope from camera number 2 in the dome. The building. Here's camera number 1 in the building. And this is camera number 0, which is the telescope computer system. So we know it's guiding, and these are the corrections it's making to guide perfectly to give us beautiful round stars. By the way, hello, Ronald. You've been here for quite a while, and I haven't said hello. Ronald is ERRT Radio, folks. He has a channel on Mixlr. Go check it out. It's called ERRT on Mixlr. He plays a variety of music, does some really cool stuff. Ronald, you can actually, if you want, you can put in your link to your Mixlr radio station if you like. And these are some of our sponsors, our patrons right now. We have John P., Izabela M., Ollie B., Chief McCyber, Vera C., Ronald T., Martin W., Raymond B., Cindy M., Terry H., Susan W., and Diane H. Ronald T. is ERRT Radio. And without our patrons, we could not survive. If you would like to join us and become a patron, we would really love that. And we're working on lots and lots of really cool things to give you as gifts for your different Patreon levels. Maybe at the smallest Patreon level, we're thinking about maybe giving you something cool like a refrigerator magnet. And at the next highest one, you could end up getting some other interesting stuff. The higher levels will get things like gym bags with a nebula on them. I have one, actually traveled with it to California last weekend to do the talk that was live. Thank you, Fantasy. Fantasy is, of course, patron. I probably should have put your name in there, Fantasy, as Fantasy. So I'm sorry that I probably didn't put it in there. I'll have to go check the Patreon list. If you added it within the last... I know you've been here a while. So if you added it, I'll have to go back and see if my Patreon list is updated. Yeah. Notice the details coming out now in this beautiful nebula. Okay. Yep. Cat's Eye Nebula. And it's a PN, a planetary nebula. All right. So we can actually show that now. Bink.
Posting a link
All right.
for the Cat's Eye Wiki in chat.
Okay.
Folks, if you go there, Gladys, we were talking about assigned colors, false color and stuff. There's a couple of famous images shown there. One is by the Chandra X-ray Observatory, and because it's in X-rays, well, all the colors you see in that image are assigned colors. But what you see in those professional images is lost in the very center of this nebula, which is just the bright blob we see in the very center of it in the image here.
However, I can give a hint, because I can actually draw out and draw down. But see, we're doing a 35-second exposure. I'd have to do a much lower exposure to actually see the core of the cat's eye and what it's really doing in there. And be fascinated as I am with the fact that there are so many stars. Let's do a color correction here. We're still getting some of the light here. That's okay. And this is right here. This is about the size of it right here. All right. Okay, so... All right, there we go. Fascinating. Cat's eye is amazing. Okay. All right, so this will be the cat's eye. If I could ever spell it right. All right, and it's a PN for planetary nebula. All right, and we have taken 21 shots, and we will save it now. And then save it exactly as seen, so that you can go download this exactly as you see it from the server. Incidentally, folks, if your screen has blurry controls or blurry letters and numbers, please go change your stream to 1080p. You should be able to do that. Okay. Beautiful. Let's zoom all the way further in, because look at that, Daryl. There's some really interesting detail in here. There's a dark lane in here. There's some modeling in here. There's some interesting convolutions in here. This is a very fascinating nebula.
Look, we have a
Yes.
galaxy over at 9 o'clock.
Yeah, remember I mentioned that earlier? I said there's one here, and then there's one over here. Let me back out and show you the other one that we said.
Right
here.
Yeah.
Yeah. Yeah, that's something else. Okay. All right. We'll just do one more save. We've got 25 now. That's a good number. And we'll save it exactly as seen. And this will be available on the server in just a few seconds. And Izabela, thank you for putting that up there, by the way. All right. So now we're going to go back to our night vision mode as we go for the next object. Actually, let's come off that for just a second. Here you can see now some more detail in the middle here. It's just, we're up at a couple 100% here, so we're a little bit more. The next telescope will actually be able to show you this a little better, actually. So that'd be pretty cool. All right, so night vision mode. Dink. There we go. Back out a little bit, and we'll do another focus adjustment shortly. I have the temperature compensation on, but I'm going to take it off because we're going to do a refocus. In fact, before we go to the next object, we'll do it right now. So I'm going to defocus this. As you can see, the stars turn into donuts. And when we do that, by the way, you can actually see the colors of the stars better. Like here's an orange star. Okay. Here's an even more orange star. Okay. They're about the same. So now I'm going to do a scan to try and get the focus to perfection, and you'll watch it change. You'll see the squares on the screen. It has 5 stars now that you see over here, and that number is going to increase as more stars focus. You're only seeing a small portion of the overall field. Okay, we're up to 10 stars, 20 stars suddenly. Okay, 21, and it's going to try and do the focus now. 40, and a satellite to mess things up. That's a Starlink satellite. Izabela, thank you for putting that link up. All right. So it goes from out of focus to in focus, and it's going to make a curve down here. The curve's going to have a slope in it, so it's going to look like a parabola when it's done. And that parabola is going to have a lowest point. That lowest point is the point where it's the highest focus. It's going to create a line through here, okay? And at the center, the lowest number, all right, is where it's going to, there it is. Did it right now. It put the center line right on that curve right there. And that is our best focus point. So we'll say best focus. And now the telescope is going to crank all the way back out and then all the way back in. All right, when it gets there, boom, we are now critically focused. It really is quite clever. All right, so now we're focused. I'll get rid of the focus adjustment, go and turn on the temperature compensation. All right, and now let's go look at another thing while we're in the neighborhood. And right now it's about 10 o'clock out there. We might, while I'm here, I'm going to do something else. I'm going to bring up our crosshairs, and I am going to move the telescope south a little bit. Do one more. We're magnified right now, that's why it looks as big on the screen as it does. Okay, do one more. And one more. And then we'll just go jog to the west one little bit. One more little bit. Center it up. Okay, there we go. That's close enough. And then we'll come in here and you'll see a difference from where our crosshair is that it thinks the telescope's at and the cat's eye. This is our field of view. It's 2 degrees across by 1.5 degrees tall. But we're seeing just a small piece of it. But what I'm going to do now is I'm going to synchronize. So this is now going to go to the center. All of our numbers change everywhere because we are now synchronized. So I will get rid of this. All right. So if we zoom out, you'll see that we are in the center. There it is in the center. All right. This dimming in the middle is due to our flat field that we're using. And we'll go to 50%. And now... Okay. Now what we'll do is... I'm going to see right now if it's high enough. What I want to look at. I mentioned this to you this before, Daryl. May not be bright. It may not be up high enough right now. Well, let's give it a try. If it's not high enough, we won't be able to image it, but that's okay. We'll just come back to it. So we're just going to drop down. See, the telescope is going to be heading down over here. But we might just make it. There it is right there. So what we're going to do is move it toward the center. So we're actually going to move the telescope toward the east. We go just about a few more chunks here. That's good, as you'll see why in just a bit. Now we're going to see it's searching for guide stars now, so some of these stars will become guide stars shortly. And we're going to expose this and see if we are missing the building. It looks like we are. So it takes about 14 seconds to acquire our guide star, so moments from now we should start seeing numbers here. There we go. Okay, so now what we're going to do is we're going to do a 40-second exposure of this right here. And we're doing it at a gain of 250. Normally we would do 3 or 350. We're going to do it at 250. And we're already exposing. So we can come out of night vision mode, go into our stack and clear the last stack. But you get to see our object one more time. That's pretty cool. That's really neat. And yeah, so that's all up there now. So enjoy that one. A lot of detail in that, Daryl.
Sorry, yes.
Yeah, I thought you were muted.
I was.
Okay. So now what I'll do is I'm going to pop out a little more. Show the whole thing. Alright, so now you'll see that this is sort of a dust cloud. and you'll see something else over here. It looks like more dust. And you'll see something right here. It looks like more dust, and some more here. This entire region is full of dust. We're going to color correct, right? And now we're going to process and start to see it. Now, as we stack more, and when I say we're stacking, what we're doing is we are taking an image. Oh, thank you, Starlink. We're taking an image, and then we're taking a second image, putting it on top of the first, and aligning it to line up all the stars. And then we're going to keep going, create an image sandwich. And that image sandwich at the end is going to make it so that we have a amazing stack of images that will be devoid of the noise you see in here now. All right, let me zoom in to show you that noise. Okay, so when we zoom in really far, you can see that in cases where there's a lot of data, right, you can see how the noise is less, right? And the color noise you see here, all right, you'll see how it gets minimized from the stack. But where there's a lot of brightness, you don't see any of it. So we have to make the brightness of the dark areas come up and get a little brighter. And that's what we're doing by stacking. All the darker areas get more and more data and become less and less noisy. And it looks better when we zoom out initially. And in just a few minutes, this entire scene is going to appear a lot different than it looks here. Ah, Starlink. Well, we're getting good service tonight, aren't we? Now, that only appears on one frame, so over time, that's actually going to get destroyed and removed. It looks like a cone saying, "Look at me." Pretty cool. Right. Yeah, this is really cool.
Excuse me a moment, please.
Yeah. So we're going to let some more come in, and then as we do, we can start to process a little and show you what this could really look like. There's a lot more data out there than you realize. So what is this? This is a nebula, okay? You see that there's a bright star in here, and the star is illuminating this nebula. Now, it's illuminating the nebula, and it looks blue, doesn't it? Well, that blue color is because the star in the middle isn't hot enough to ionize hydrogen gas out here to make it a red nebula, but it is bright enough to scatter, or so the dust is actually there. This is mostly dust actually in here. But there is some hydrogen gas mixed in with this, and you can see subtle red around here. But this dust doesn't ionize the way oxygen and hydrogen do. So we don't see a red glow or a green glow. What we see is a blue glow. And that's because, let me zoom in on this. That's because inside this nebula, all right, you can see all this detail in here. This is all dust in here. It's a very dusty region of space. And inside this nebula, that star's light has the entire spectrum in it: red, orange, yellow, green, blue, indigo, and violet. But the blue light is very, very short wavelength, high energy light. So these dust particles are tuned to just about that frequency. So when that light strikes the dust particles, they absorb it and then re-emit it right away. All right? But the rest of the light is allowed to flow through somewhat unimpeded. So that's why when we see dust like this illuminated by stars, the dust is actually looking blue only because it's scattering the blue light from the star and letting the rest go through. Okay, so that's what we're seeing. And by the way, that blue is the same blue that you see in your daytime sky. And it's for like the same type of reason. It's called Rayleigh scattering. And it's a scattering process. So in this particular nebula, you can see there's a vast dust cloud over here, there's more over here and everywhere. And this dust cloud has one star in it that's local to it. The rest of these stars are either far in front of it or far behind it. But this one star is illuminating from inside this dust cloud. And that's what makes it so incredibly cool. So this is neat. Now this is low to the horizon. When this gets higher, it'll be an even prettier object. So let's do this. Let's just play with these data values a little bit. That's pretty cool. You'll notice, by the way, over here, right here, there seems to be a little oblong-y weird shape opening, and you can see the stars behind it. You don't see the stars behind here. You see some poking through, but there's all these stars in the same density behind and through this cloud. However, again, zoom in, right? As we zoom in, all right, you'll see that this is a hole, and we're looking through the hole to the same number of stars back here as there are seen through here. But this area right here is being effective blocker of the starlight behind. And when they do peek out, their light is reddened because, again, their blue light is scattered. And so what comes through is something that's more red, just like you see at sunset. If you have any questions, please feel free to write them. Welcome back, Daryl.
Thank you. Michael Hedrick, bright stars that appear to change colors a lot. That's just the stars twinkling. That's atmospheric disturbance.
Scintillation, yeah.
Scintillation. We call it SIG in astronomy. How steady the air is or how disturbed it is. If you see the star Sirius rise in the winter sky, it's a famous twinkler. I always thought that's one reason it's like a good Christmas star. It sits there and changes color constantly, but
that's right.
It's all atmospheric effects. It's just the air is moving, the refractive index is changing moment to moment, and sort of like the colors in a prism, you see the colors of the star change. And it's all twinkling is all it is. And per that, Ronald, your question that maybe brought that on, variable colored nebula that changes colors. There are nebulas that have multiple colors, but I wouldn't expect the color of a nebula to change in and of itself because they're large objects and those colors are coming from various gaseous elements. As we've talked, like green is oxygen, red is hydrogen, sometimes like neon. And those clouds are so huge, you're talking like light years across, that they're not going to sit there and just, change colors randomly. They're going to give off characteristic colors of the elements inside the nebulas, and they're going to be constant.
Yeah.
If you see pictures like of the Orion Nebula, you'll see red, you'll see blue, you'll see red, you'll see green. It's mostly
Blue,
hydrogen
yeah.
and oxygen, and those colors are constant.
Yeah, and the blue is from the scattered starlight we talked about before, guys.
Yeah.
Now, hello to Curtis Horn, who just joined us. Hi, Curtis. Thank you for joining us tonight. Now, as I said, this object is still kind of low. You look where the telescope is aiming right here. It's way over aiming into the northeast. So we're looking through more atmosphere at this nebula right now, and it's only going to get better as it rises. But we will actually, we want to preserve this. Look at how detailed this is in here. This is really getting pretty, and there's so much more detail in here. I'm going to kick this one up to kind of give an idea. Okay, you see how much more detail is out here. There's all kinds of dust in here. You know, and when it gets up higher in the sky, we'll be able to see that very clearly. But for now, I'm going to call this the Iris Nebula, because that's what this is. And it's a DN, a dark nebula, and an RN, a reflection nebula. Alright. And we've done 18 of those. We're going to save it at that. We've seen it so much better. But there we go. We'll correct it one more time. See if it changes much. Oh, see, now we've gotten a little bit more data. We can start to see the reddish brown coloring, because I mentioned how there's hydrogen here, and so we're getting some hydrogen ionization, but we're getting mostly dust that's scattering the starlight and making it look blue. So that's actually worth another save, but it may not let me. Okay, very good, we could. So I'm going to save it exactly as seen. Here we go. Very nice. And this will be up there for you to grab on the server. And where's the server, you may ask? Well, the server is right here in skytourlive.org. You head over here to skytourlive.org, and I'd be pointing at it right now if my camera was working. Skytourlive.org will allow you to capture and download and view these images just like we see them here. All right. Now, the other thing I have to look at. This is a large nebula. It spans a few light years. But I'm looking at this feature right here. You see this long line right here, Daryl? I think you muted again.
No.
You don't see that line?
No, I'm
dark
not
line?
muted.
Oh, okay.
That
dark line?
There at about 5:30 to the main star. Looks like a
Oh,
dark
come on,
line,
Starlink.
the thin light line just above it.
Yeah, there's a dark, thick line up above and a lighter line just below.
Okay, yes, I see the thin dark line, the thick dark line,
Yeah.
and maybe a thin light colored line above the big dark line.
Yeah, I see that too. I'm wondering. I don't remember that feature, but it's probably there. But I would like to see if there's been a change to that, because it's a very, very large nebula. But there are nebulae, and here's the thing: although they're vast clouds of dust, they would have to move at very fast speeds in order to change, from our perspective. And that speed would have to be light speed, so they can't do that generally. But what we do get are nebulae that change in brightness. A famous one, as Daryl has pointed out and I pointed out, is Hubble's Variable Nebula. That's something that is in the winter sky more than the summer sky, of course. And so there are more than one variable nebula out there. And it's because there's a dark cloud like this, and inside the dark cloud's a star, and there's some dust orbiting the star. And when that dust clears for a moment, as the dust orbits the star, it might go to a less dense location, and the starlight will show through brighter and illuminate something like more dust a little bit brighter than it might normally. And then when that dust rotates around again and orbits, it may block more of the starlight from the cloud, and the cloud will suddenly get darker over a period of a few days. And that's what we see with Hubble's Variable Nebula. Fascinating. All right, let's get out of this now.
Yeah, I don't know about those features in particular. As you said, I mean, the scope seems to be working very well. Maybe we just didn't notice them before.
Possibly, yeah.
Go back and find old images of the iris and compare them.
Yeah, that's what we do. We have lots of these good images.
Yeah.
Okay, so we're good here. We've got those images saved. And now we're going to come back to our wonderful night vision mode. Okay. Now let's go back here. Now there was something else we wanted to look at, and that's something way on the other side of the sky. And we're going to see if we can see it yet. It goes way over here, coming all the way around, and heading all the way to here. All right. We have Scorpius.
There's the teapot.
Yep. Sagittarius is rising right here. Sagittarius, the archer, is seen here in our mythological view. There's Scorpius the Scorpion right there. And Scorpius is one of those few constellations that actually looks like what it is. You can see this scorpion right here. Yep. And we're going to actually go check out this guy. This is a globular cluster. And you watch the telescope and it's going to swing all the way around to the other side of the sky. Right? And there we go. Off it goes. And we'll see the globular cluster show up here in just a few seconds. I think it's high enough. And we'll see Antares as well. Oh, look at that. There it is. I forgot I had zoomed out. All right. So,
Can already see that sort of vertical bar of stars across the face of the cluster.
I know, huh? So as I move it over, you're going to see that cluster centered up. Antares may come into the view, but I think it's going to stay out of the view at this point. Okay. Beautiful. And this is Measure 4. It's really quite nice. And that vertical bar of stars that Daryl's talking about is right here. That's just a line of sight artifact, possibly through gravitational interactions. They orbit each other. These stars have been orbiting each other for billions of years, and they're among the oldest objects in the universe. So what we're going to do is we're going to set up for taking a 25-second exposure. That's really all we need. And we're going to wait for our guider to start counting down numbers and actually show us. Izabela says Starlink is framing it now. Yeah, I know. But that's the way it works. Cryptasia says, no way, it's Elon Musk's Starlink. I don't know why you say that, because I'm actually quite certain it is. Alright, we're guiding now. We get those diagonal satellites coming through, and for a 1 second exposure that we do, when we're zoomed out like this, you see the length of it, and the length of it is a classic length for the Starlink satellite trains. when we were in California, you didn't get to see this, but when we did the live audience event in California with those several hundred people out there, I was looking in the sky because I knew something magical was going to be happening that they were going to see, and sure enough, we saw 25 Starlink satellites right after the ISS. We saw the ISS, and a half hour later, we saw 25 Starlink satellites in a train. Okay, we're guiding now. We're stable. Let's now tell to go.
Mohammed, we're looking toward Scorpius.
Oh, and hi there, Mohammed. Thank you for coming in. Let's welcome Mohammed Akbarshan. And Kay.
And Saber Circer.
Saber Circer. All right, let's get rid of this guy. That's too much.
Circer, I think.
Saber. And Dean Bustador is with us. All right, let's color correct. There we go, and then let's do this. All right. Now we can probably remove our enhancement for this one. It's kind of rounded out a little better. You notice this red up here? This is a nebula. This is a hydrogen gas cloud that's been ionized, and it's actually glowing because we're now near a very famous, it's north of this, but it's a very famous location called the Rho Ophiuchi complex. We might be able to take a picture of that tonight, Daryl. Low as it is.
That bar was first observed by William Herschel.
Oh yeah, I betcha. That bar is this thing right here.
Yeah.
And I might, if I can pull away some of the brightness here. Let's just drop the brightness in the core just a little bit to help accentuate that bar. Okay. And we'll zoom in.
This is the closest globular cluster to Earth. 6,000 light years away.
That's why it's so large.
Yeah.
Let's jump right into it. Beautiful. Now we come out like this. Here's the blackness of space, probably dark nebula here. And then right to its lower left, there's more cloud. Up there is more cloud, and here is more cloud. This is hydrogen gas clouds, dust clouds down here.
Another
really,
globular
really nice.
to the top left.
Yeah, that's right. That's the other one that's then in this field of view. Let's identify that. So if we zoom in on this. Okay, let's center up on this. And zoom in. This globular right here, that's up in the top left, is NGC 6144 or Melot 147. That's what the Mel stands for. This is our field of view. See how the numbers are upright? So if this is the globular cluster here, we actually have this cluster up there, and we do. Right, so what we'll do is we grab this M4, and we're going to synchronize our telescope one more time. There we go. Gladys says it's like a little tiny speck of glitter. It is, isn't it? Really pretty. Now the other thing too is we're seeing a little bit of the Alnyat Nebula, and then a little farther north is the beautiful blue of the Rho Ophiuchi Nebula, which we'll check out because that'll be in a little better position. Alnyat, actually, I'll take a picture of Alnyat too, because that way we can test some of our processing that we want to try and collect things with and remove some bright halos. And right now, Izabela is saying, ooh, the remove function in Photoshop. Yes, that's right. I'll take something that really needs it. We'll see how it works. We'll be testing that. Yeah, so you see all this red. Huh?
There's a lot of nebulosity around Antares as well.
Oh, I know, but Antares is so bright.
Yeah. When you see Antares, folks, that's the heart of the Scorpion.
That's right. Let's go to the Stellarium and show them.
It's actually very much like Betelgeuse. Antares and Betelgeuse are probably the two best candidates for supernovas in our part of our galaxy.
That's right.
At least that we can see easily. They're very similar. They're both red supergiants.
If you put Betelgeuse where the sun is, it would go all the way out to Jupiter, and the distance from the sun to Jupiter is 5.2 astronomical units, I think. And so that means that Betelgeuse is going to be 10.4 astronomical units in diameter. That's a lot of hydrogen, a lot of other elements. Incredible. All right, so this is beautiful. So what we're going to do is we're going to drop it down. We'll get Alnyat in the picture, and then we're going to take some similar exposures. I did 15 here. We'll do the same thing there. M4 Globular Cluster. We'll say save. And save exactly as seen. Just beautiful, isn't it? Welcome to the stars of summer, folks. All right, and now we'll
one of my favorite clusters.
I know, because it's so close and so beautiful.
Yeah.
All right, so now we're going to take this and drop it down. All right, and to do that, we're going to head north. And there's Alnyat, okay, and I'm going to bring this down to about here. All right, and I'm going to move us a little west. Okay, that's good. Maybe a little more down, because we're going to make this a mosaic. You'll be able to make a mosaic out of this. But we'll do that for you. And if I know Izabela, she'll probably try and do it before we're done. It might happen. But it's 1:37 in the morning right now, so we have to, not rush summertime. It'll be here soon enough. Okay.
Mark, could you, I'm sorry, while you're setting up your shop there, can you open Stellarium again for a second?
Yeah, let's just do another shot here. Let's do 40 seconds here.
Okay.
And then do our stack where we're exposing. Okay, so there is our last shot. Now we're up here near the top, past the top. And let's clear this. And once that clears, let's go into Stellarium.
Okay, can you back out a little bit?
Yeah.
So we can see the whole Scorpion. And Libra up to the upper right. Gladys was wanting to see stars in Libra.
Libra's a very boring constellation.
Well, I was going to show her what makes it interesting.
Okay.
Gladys, if you see the star there at the top of the scale, and at the bottom of the scale, those are the two stars I was talking about, Zubin Janubi and Zubin Shamali. Zubin Shamali is the top one. Zubin Janubi is the bottom one. In ancient times, before the constellation Libra ever existed, Shamali and Jamali, Shamali and Janubi, they were the tips of the claws of the scorpion. You see, if you extend from Antares, those three arms coming out, those three stars, they extend out toward the two bright stars in Libra. And those represent the arm. In the old days, those represented the arms and the claws of the scorpion.
It's a big scorpion, man.
Yep.
Very cool.
Yes, it was, Gladys. A very long time ago.
I'm not putting down Libra, Gladys. I am a Libra.
I'm sorry?
I was saying to Gladys, I am a Libra. I'm not putting it down.
Oh.
Alright, so here's Alnyat, and look at the nebula around that. And let's just do a little color correction, which I think we've got done already, but it's going to make it a little more red. Now look at this. Look at that. Wow. Isn't that incredible? That's really pretty. Hello, M. Turner. How you doing? That's really stunning. Oh, yeah. Of course. All right, now that's looking really pretty. Let's just richen these colors. This is really cool. Look at that. That looks really pretty. That's something. Well, so this is Alnyat, okay? And, or Alnyat. And, you can see these beautiful hydrogen clouds of gas that have been ionized. And what's in between is dark nebula. This is dark stuff in between. It's not an absence of stuff. There's a lot of, especially toward the center of the galaxy in this area, there's a lot of dark dust between us and that area. And that's what we're seeing here. Really nice. Isn't that really cool looking? And as time goes on, we're going to get even more detail. Let's see what else is there by hitting this other histogram over here. See that? There's a lot of stuff out here. There's filamentary stuff, filaments of dark nebula, bright nebula here. Remember, we were down here, a little bit lower in this view, and we're seeing just the remnants of Messier 4 right here, that globular cluster. Okay, so that'll make an interesting mosaic of these two regions. And of course, there's so much. You could just do endless mosaics of the whole Milky Way. I'd love to do a whole Milky Way. Yes, Izabela, she says, this indeed is a very good test for the removal tool. What are we talking about? Well, you see this halo? That's an artifact created by the system. the camera system, and no one likes these artifacts, but they live with them. Well, I don't want to live with them. I want to get rid of them. So there is a tool in Photoshop called the removal tool, or the remove tool, and you can just wipe out this thing without losing what's behind it. That's kind of it's like an AI type thing practically, and we want to do that. Now I turned off. See, if you pull this down, then you'll see it more like you'll see it through a modest telescope. All right, but you bring it up.
You're actually seeing an image of the front corrector plate.
Yes,
and
this is, yeah.
The camera on the front of the telescope and the two cables coming off of it there.
Yep. Yeah, what people don't realize is that on our telescope, the camera's in the front. It's not in the back like traditional telescopes. In fact, in our telescope here, if we just zoom in for a sec, okay, that's where the camera would be, all right? But on our telescope, that's just a counterweight because the camera's sticking off the front of the telescope up here. So that's actually quite a problematic thing when you're trying to manage the front end of the telescope. You don't want anything blocking that light, but there's a little bit being blocked, and that's okay. Michael Hedrick says, may I ask Mark or Daryl, what percent of naked eye objects are visible because they are close, and what percent are visible because they are big and bright? Could you both answer, please? Oh no, he's got us. Well, I'll go on this one too. I don't know the actual percent. That's probably published out there somewhere, but we see a mix of objects. We can see, for instance, galaxies with our naked eye. Okay, the Andromeda Galaxy is one of them. It goes several degrees across the sky, and yes, that's the one that's heading for us in a couple billion years. And then we see the Orion Nebula with our eye, and that's a gas cloud 1,500 light years away. Andromeda Galaxy is 2 million light years away. So we can see to very different, I guess, distances in space. And Daryl, you can now fill in your piece of that if you'd like.
There are a lot more dim objects than there are bright objects in the sky. The dim objects, the really dim ones, are red dwarf stars. We can't see at all naked eye,
Right.
but there's a ton of them out there. There are a lot more
there.
dim stars than there are bright stars. But the bright stars stand out, so we tend to see them even though they're farther away. Some are really far away, like the stars in Orion's belt, or all the bright stars in Orion. Well, Betelgeuse is 650 or 700 light years away. The belt stars are maybe 12 to 1,500 light years away. When we see the brightest star in the sky, Sirius, Canis Major, it's a moderately bright star, but it's only, 8 light years away, 25 light years away, 8 light years away, I think.
I think it's 8 for Sirius.
Yeah. So it's a pretty bright star, but it's pretty close to us. How would I answer your question in a big way? Like Mark, I don't know where you'd break it down at. The bright things we see probably tend to be farther away, but you're talking different scales too. The naked eye planets we see are middle and bright to bright, but they're all inside our solar system and they're quite close to us. Our star is bright and it's only 8 minutes away. The moon is bright and it's only a quarter million miles away.
Right.
The brightest star is 8 light years away. There are bright stars out there that are thousands of light years away. It's a continuum, and I don't know where
Now,
you
you
draw
might
the
wonder,
line between what's close and what's far.
yeah. And you're wondering what I'm doing. I'm outlining all the potential faint stars that we need a telescope to see. Those are called M stars. Their temperature is very, very low on the surface. They're only about 2,800 to 3,500 Kelvin, which is a temperature scale, or just a few thousand degrees. And many of these stars are so small that they would be invisible in all but some very modest-sized telescopes, including this one. So now the red could also be because of extinction. That is the process by which the star's light is reddened, and that is something that could be happening here as well. All right, but what I want you to get out of this is that as I do this, you'll see that I'm probably going to be outlining almost all the stars in here, because many of these stars are red dwarfs. These little red stars, only slightly larger than Jupiter, and putting out 100th the amount of the radiation of the sun. And those are the stars that have the most planets around them in the entire universe. Are these M stars? The only problem is the M stars are somewhat unstable, and they too tend to be flare stars. But we're actually capturing them just like this. This is what we see. So, and there's so many more than what I'm showing you here. So, there.
I have a challenge object for you.
Okay.
Barnard star.
Yeah, Barnard star.
It's in Ophiuchi, I believe.
Yeah.
Well,
let's.
Ophiuchi.
I want to do a Rho Ophiuchi. Shot here. There's 20 of these taken, so we're gonna save this after I call it Alnyat, or try to anyway.
All right. Now that I think about it, I think Barnard stars in Stirpins, which is near Ophiuchi,
It's not
but
quite
it may
there
not
yet.
be high enough to see yet.
Yeah. All right. So now we've done that. So what I'm going to do now, this is Alnyat. So now I want to take us up to, it'll be the last object for tonight because it's almost 2 a.m. First of all, we're going to go into night vision mode. Now what we're going to do is head up to the Rho Ophiuchi Nebula.
Barnard star is in Ophiuchi. I'm not sure where. Okay. It's a big constellation.
Yeah.
Maybe next time. Or we'll have all
right.
summer long.
Indeed. All right, so we are...
Barnard star is a classic red dwarf, like all the little red stars that Mark was talking about.
Yeah.
When he was looking at Alnyat.
Alright, so we only have to move just a little bit to get to here. So we're going to do that now. If anything, we're going north, it's going to be easier to see. But you see all this dust? We've got lots of detail in here Now, Rho Ophiuchi is going to see two stars here. There they are. And once we're in place, we can drop the telescope a little south. Not too much. Or for this first look at it for the season, we'll do it this way. And you're going to see that there's lots and lots and lots of stuff hidden inside all of this. This one I'm going to make 45 seconds. And we're going to go to 300 gain. So we're going to actually get more detail here. So it's underway. And we're going to call it Rho Ophiuchi Nebula. And we're going to come in, do this, and no. And now we're going to clear this.
Are you zoomed in right now?
I'm at 30%, so no.
All right.
30% is approximately the full frame. Okay, so now we're going to get rid of this guy over here. Don't need that histogram. And now we're going to do this right here. And look at that. There's a lot of beautiful nebula here. So everything in here you see is dark nebula punctuated by these reflection nebulas that we call them, the scattering nebulas that we talked about, where the dust grains in here scatter the blue light from these stars. Izabela says, Rho Ophiuchi means summer to me, and Orion means winter. Yeah, same for me. Same. So very, very well spoken, Izabela. So there's so much more below this, okay? And you can see down here there's so much more. And in subsequent visits, we will actually show that. This looks ghostly when processed. I mean, it really is just incredible region. I just want to officially welcome Rho Ophiuchi back to our sky. Welcome. We've been looking for you. Now, that dark dust you see, that's dark stuff, you see how it looks filamentary and wispy? That's all supernova debris. All of it. It's debris created in supernovae, right? And so it's also the result of aggregations or combinations and collections of very, very small atoms to make particles, which then make dust. And that's what we're getting at here. Hold on 1 second. Oh, let this go. I'll be right back. Be right back.
I'm going to drop a link in
Okay.
chat.
Look at this. Look how beautiful it's shaping up. Oh, sorry. I didn't realize you were talking. I apologize.
This is of, it's a nice photograph of Ophiuchus, Rho Ophiuchus in particular, but it shows the toward the center of the Milky Way also. And it's directly above Antares and Antares and M4 and Scorpius. And you see the dark streamers extending over to the left, all the way over to what constitutes what's called the Dark Horse Nebula, a little bit left of top center, and the Pipe Nebula, which is just close to the center of the galaxy. It's a beautiful picture.
Yeah, and we're gonna remove the name. I mean, the name can come back, or I'll get rid of it. I just want you to see it. In this image, there's something to note right here. First, we have that beautiful reflection nebula we talked about. Over on the right side, we have a hydrogen glowing gas cloud, an emission nebula. Then we have these beautiful streamers of dark, beautiful dust that are in here. So that's dark dust that doesn't have a proximity to a star that can get its light scattered by this dust. So look at the streamers, the way they go. And the more we do here, the better it's going to get. Okay, this is only 6 stacked images. But that's an idea of what we're looking at right there. Look at all that dust in there. That's really pretty. And I want to ask Izabela in particular what she thinks of this. I think I know her answer. It's just beautiful. Another test for our remove tool. She says it looks like the face of a sleeping woman. I don't see that, but I'm sure you could. Isabel's an artist, by the way, a very good one. So I'm an artist too, but she sees a different type of things than other people, and it's really interesting listening to her.
Izabela sent me, or she posted in her Skype the M4 Alnyat.
She already did the. She already did the mosaic. Well, let's show people what it looks like.
I'm trying to get it over to you now.
Okay.
Stand by.
And once again, this is the Rho Ophiuchi Nebula. Okay. And we're taking these pictures live. This is the universe, live in real time. Thank you for joining us, those of you that have.
Well, darn it. Bear with me just a second here.
Yeah. Notice how as the stack increases, we have more detail now. Look at this filament that's actually making itself very evident. In fact, why don't we do this? Why don't we get rid of the stack information for now? And why don't we get rid of my telescope for now? And let's just do this. And just go to the big time. What do you say? There we go. Look at that. So that'll be developing over time. We'll see any remaining noise will go away here before long. We can always bring this up and make an adjustment right here. Pull this down a little bit. Make it more subtle. That's beautiful. And to see what else is there, we can just pump up this histogram. And there you go. Now you see that it's mostly dark nebula in here. And that will be visible in our final image. But what a beautiful location. Hey there, Prow. Oh, Curtis Horn. He says, great show, Mark. By the way, I picked the EAA. I missed that. Oh, EAA Challenge Objects of the Month on cloudy nights. EAA forum if you want to check them out for a future broadcast. That's really cool. Nate says this looks very nice. It hardly ever disappoints, Curtis. Hardly ever disappoints. Oh, by the way, you might notice it in our chat sometimes. You see Michael Tarr. Michael Tarr works at SpaceX. And I was in California in Palm Springs, and he showed up, and I got to meet him, and his significant other, and she's a really, really, really nice lady. And it was actually very nice to meet some of the people in STLS, SkyTour Livestream, in person. Very neat.
Mark, I dropped that image in your chat.
Oh, you did? Okay. All right, let's go get it.
It's M4 plus the Alnyat nebulosity.
Yeah, let me see where that is here. There we are. Okay. Let's bring it over here. Because of the way I streamed and put this together, Daryl, you may not see it, so you'll just have to bear with me on this. Actually, I know you're not going to see it because I'm showing you a window. All right.
Yeah,
but
I just see a big.
I'm just going to show the right screen right now. Oh, well, it doesn't want to do the right screen. How about that? Well, until I figure that out. Oh, of course not. All right. Well, it's developing now. Our image is developing, so let's just let that happen for a few minutes, and I will see if I can show this.
Popped up on my screen with you for a second and went away.
Yeah, no, that's okay, because they're seeing the broadcast. They're not seeing what's on my screen. But that's all right. I'm going to have it up in here in a second, actually. Probably in a better way. Okay. There we go. All right. So that right there
Yeah,
is what it looks like.
See it on YouTube now.
Yeah. Yeah, that's what it looks like. So that is the stunning and beautiful mosaic of Measure 4 and Alnyat. And above it, a little to the left, is, of course, where we are right now, which is here. This is not Alnyat, I don't believe. Pretty cool, huh? Now you can see this nice feathery looking dark nebula down here, which we couldn't see before. You can also see subtle light and dark shadows on this dark dust here, making it appear 3D. You can also see this red star buried in this dark cloud, and it looks like it may be part of the group that's illuminating this dust as well. Amazing. This is nice.
Pretty picture.
Dean says he sees the sleeping woman. Do you see the sleeping woman?
No, I don't.
I do not. Let's see if we can... Let's see if we can force her to be more apparent. Wow, look at that. Hello, Rho Ophiuchi. It's been a year. So anxious to see you again. This detail in here is just exquisite. Look at all those knots of dust. It is just beautiful. Very, very nice.
I want to see the sleeping woman. I like sleeping women.
Izabela, I think you can help us out with that. I'm going to redock this now. And let's do a little enhancement here. Hey, Prow, me too. He says it's after 2 a.m. for me. Yeah, it's after 2 a.m. for me too. I'm on the East Coast. But unfortunately, when summertime rolls around, early on like this, we have to stream starting around midnight when it's dark enough in Arizona to see what's going on. And then it's only in 12:20 a.m. that it's dark enough out there. There's Rho Ophiuchi right up here. This is stunning. Ugh. Let's go back to bringing this up like this. Okay, let's save this. There's 22 stacked here. So we'll save it just like you see it. And now this will be up on the server. Face is down in the lower center of the screen, Izabela says. Is the face down here, Izabela? Maybe you're right. Maybe you're right. Okay. Nice.
I'm turning into a pumpkin here.
I know. I'm almost done. We're going to go to 25 shots here, and then we're going to call it. I hope you guys have enjoyed this, because it's been a wonderful evening. To end with such a brilliant object as this, it's really something. And again, it's the Rho Ophiuchi Nebula. Okay, 24 frames. We'll save it there. One won't make that much difference. So we'll save exactly as seen. Well, there you go. Alright, well, on the next clear night where we don't have to worry about a moon, we will come back and do more of this. And all we have to do is wait another week or so, and there'll be some prime time objects to check out. Before I go, I want to zoom in down here. I let that settle out a bit. Look at that. See all those orange stars? most of those are reddened by the nebula through which we're seeing them, but many of them are those red dwarf stars. Very nice. Okay, there's 25. All right. All right, folks. Well, hey, thank you so much for joining us tonight. We checked out the supernova, and then we started going through some of the onset of summertime objects. So I hope you guys have a good night. And you know what? We'll be back. We'll be back because I can't stay away from this stuff. And Daryl can't stay away from this stuff. I bet you dream of this stuff like I do.
Sometimes.
All right. Well, good to see you, PG. I don't know if I said hi to you, but it's so good to see you here. All right. Well, you guys have a good night, and we'll talk to you soon, all right?
Good night,
So
everybody.
we'll see you later. Good night, everybody.
Good night.